self-induction, opposition of change of current taking place, for example, in a loop by the loop itself. Loop itself opposes the change taking place in current through it. And why does it do so? Because if some current is flowing through it and that current changes, then flux changes. And change in flux is opposed. We know how Lenz's law works. The different way of looking at it is that if you change current, then because of flux change, there is induced electric field, due to which there is induced EMF, and that EMF has such positive negative terminals which oppose this type of thing happening. We can say that the total flux is proportional to field if area is constant, and if there is nobody else contributing to the field, only that self is there, then field is proportional to current. So we can also say that flux is proportional to current. So we introduce a constant to get rid of proportionality sign. That constant is L. That L is called self-inductance. It depends on the geometry of the system we are talking about. As you will see later, when we find L for solenoid, you will see that L for solenoid depends only on the construction parameters of the solenoid, the geometrical parameters. So for one particular coil system, no matter how you orient it, once it is decided that this is your system, then L is fixed for it. In place of phi, we put Li because L is constant. I mean, it is constant with respect to time for sure. It will come out of the derivative. So we have induced EMF equal to minus L di by dt. I am talking about a conducting loop. Now, you can also find E by writing phi as integral B dot dA. For n terms, it will be n times integral B dot dA, derivative of that with minus sign. That also you can find E, and the two ways E has to be equal, whether you do it this way or that way. In fact, this is the way we find L for some system. We say that E is minus d dt of n times integral B dot dA. And we also say that E is minus L di by dt. This is how we find L. So I will illustrate how we find L, but any questions up to this point, let me know. Just think of L as some sort of inertia. Maybe electromagnetic inertia, you can think of it as. So let me give you an illustration. How do we find L for a particular coil system? In fact, why do this whole thing? I mean, this is same as this and is constant, so this is same as this. So why not write one more step? Minus n times d dt of integral b dot dA is equal to minus L di by dt. So this is same as writing n times b dot dA. Integral equal to Li. Basically integrating both sides with respect to t, that's it. Or in very ordinary language, multiplying by dt, both sides. But that's not a great way to think of it. Integrating basically both sides. But that will only get rid of d dt operator. This integral will still be there. But why bother getting it from here? Why not just look at this step? Look at the pointer. Phi total is Li, right? And I'm assuming that this is an isolated type of system. Like this coil is alone, nobody else is in the neighborhood that can contribute to flux. So phi total is Li, and phi total is integral b dot dA basically, and if there are n terms, you can multiply by n. So using this, we can find L. So it can be treated as a formula for L also, like L is n by I, L is n by I, integral B dot dA. If you look at n by I, integral B dot dA, then it may not be so obvious that L does not depend on current or magnetic field. L just depends on the geometrical parameters. But that's how it is. N by I times integral B dot dA eventually depends only on geometrical parameters. So let's do an illustration. We have an ideal solenoid. Some current is flowing through it. How will it react to change in current? It won't like it. It won't like it. If you try to decrease current through the solenoid, it will try to sustain it, maintain it. If you try to decrease the current, and if you try to increase the current, it will try to oppose it. If you try to increase, it will try to decrease it. If you try to decrease, it will try to increase it. So that property which is responsible for this behavior, that is self-inductance, which is just like inertia. So Li, let L be the self-inductance of the solenoid, then Li will be n times integral phi dot, B dot dA. There is nobody else in the nearby region. Whatever flux change is happening, it is happening due to the current in the solenoid itself. So magnetic field will be mu naught Ni. I is the instantaneous current. Magnetic field is mu naught Ni. Radius is R, so pi r square. And you know how magnetic field is inside the solenoid. It is along the axis. And if you take an area vector, some circle, you can consider area vector will also be along the axis. So B dot dA is simply that. Mu naught Ni into pi r square. But then this is for one turn. Let capital N be the total number of turns. Then capital N times that. So you cancel I. And you have L in front of you. But then suppose capital N is not given. Small n is given. Total length is given. Radius is given. Then what is small n? Number of turns per unit length. Number of turns per unit length. So just get rid of capital N, putting small n into L in its place, and see if you are getting this answer. Mu naught pi n square r square L. Mu naught universal constant, pi universal constant. R is the radius geometrical parameter, L is geometrical parameter, N is also geometrical parameter. How you have packed, how close you have done the windings, that's geometrical parameter or construction parameter. When we talk about solenoid in this context of electromagnetic induction, then it is called, often called inductor. An inductor is, after all, made of wires, and wire may have some resistance. So when we say ideal inductor, when we say, then it means that its self-resistance is negligible. So maybe thick and very good quality conductor is used like copper, and that too thick. So when we talk of ideal inductor, then it means that there is no resistance in it. But practically there will be some resistance. So because of this property, you really can't make current zero suddenly, all of a sudden. If current is flowing and suddenly you make it zero, that's a big change in taking place, and that big change will be opposed. Sudden rise is not allowed. Sudden fall is also not allowed. One may not realize this thing when dealing with small appliances, but in case of very heavy motors drawing huge currents, switching off may not be that easy. I mean, it may not be so instantaneous. Let me give you an illustration regarding application. In fact, before that, one point. This is how you represent an inductor, ideal inductor. If it is non-ideal, some resistance can also be shown. Suppose you have an inductor like this and current is flowing like this. And suddenly you try to decrease the current. Maybe some resistance is present in the circuit and you increase that resistance. Basically you try to decrease current. Then it will try to assist that current. It will try to maintain that current. So obviously plus will come here and minus will come there. So it acts like a battery sort of a thing with this type of behavior, negative terminal, positive terminal. If you try to decrease it, this is what will happen. But if you try to increase the current, then it will oppose that increase. Current will be disliked in this case. So this type of self-battery will be created by this fellow. So plus on the left side and minus on the right side. So current is trying to increase, battery says no. Now this self-induced battery of course will have limitation. It's not that it can fight anything else. Just like any inertia has its own capacity. A body likes to maintain its velocity, a particle likes to maintain its velocity, but liking doesn't mean it will happen always. External agent can become more powerful and can change the velocity. So this is just trying to oppose, that's it. It has its own limitation. This EMF that it is generating is basically minus L di by dt with sign. It is minus L di by dt with sign. With sign means mathematics is telling you the sign. But if you use common sense approach to get the sign, then use mod. So I have already used common sense approach to get the sign. I would say mod L di by dt. That will be the magnitude of this EMF, and that has limitation. External agent can beat it. But nevertheless, it can slow the things down a little bit. If current could change immediately, it will change little slowly now, whether increase or decrease. Yes, now we can take this. The sliding contact is being pulled towards right, so that the resistance in the circuit is increasing. Resistance is increasing. Yes, this will go to the right, so resistance will increase. Its value at the instant shown is 12 ohms. Will the current be more than 0.5 amps or less than 0.5 amps at this instant? Now this is an interesting problem. You will realize it when you see the answer, final answer. 12 ohm is the resistance right now. 6 volt is the battery. This is ideal. Take it as ideal solenoid, ideal inductor. No resistance it has of its own. It's just an ideal wire basically, but coiled, and that makes a difference. Straight versus coiled makes a lot of difference. Then if you use Ohm's law, then 6 divided by 12 is 0.5 amperes. So 0.5 ampere current is what you will say if this were a straight wire, absolutely straight wire. Right? But because it's coiled, because it's inductor, it behaves differently from a straight wire. It has got its own magnetic field, and that creates the difference. Now, induced EMF mathematically with sign is given by minus L di by dt. Here mathematics itself is giving you the sign. Okay, just one more clarification. How does this sign scheme work? Let me explain. In fact, this becomes clear from here itself. How does this sign scheme work? If current is entering, If current is entering this side, then this is the plus sign. This is how it works. I think I will have to elaborate. Common sense approach I have already told you. Mathematical approach is this. Mathematical approach is T induced is equal to minus L di by dt. It tells the sign automatically. How? If current is entering from here, put plus here. That's it. Rest leave to this math. Automatically it will take care of everything. Remember, in case of resistors, in current electricity topic, what we discussed in case of resistance, if current was entering, then this was positive, because resistance drops potential. Resistance drops potential along the direction of current. So this was for resistance, this is for inductor. But then for inductor it is about change in current. For resistance it was not about change in current, it was about the current. Whatever current is, this will be plus. Here, if current is steady, 0, 0. The 2 points will be equipotential points for ideal inductors. If there is no change in current, that won't be so for a resistor. So to decide the sign, you have the two approaches, the common sense approach, that current is falling, then it will try to increase it. So accordingly it will choose plus minus sign. That's the common sense approach. Other is the mathematical approach. If you see current entering from here, put a plus here and write E equal to minus L di by dt. This is the positive terminal of this E. If answer is opposite, math will take care of it. In this problem, I have followed the math approach. So this would be the answer if this were a straight wire. But it is inductor. So induced is minus L di by dt. Current will obviously enter like this. So this is positive. This is positive, then this is this. Minus L di by dt. Whether it is really positive or not, that math will tell. And because resistance is increasing, current has to fall. Current has to fall. So di by dt has to be negative. If this is negative, negative into negative is positive. That means whatever is the direction shown, the same will be the answer. If resistance increases, current drops or tries to drop, current tries to drop. This inductor says, hold on, I will help you, and makes this side positive. That's the common sense approach. Other approach is that current falls or tries to fall. So di by dt is negative. Negative into negative is positive. When we use the mathematical approach, we always put plus sign here if this is the current entering. And since minus minus is plus, the same thing will hold good. This will be the answer. So actually, we have two batteries in series. We have two batteries in series, minus, plus, minus, plus. Now, if two batteries are in series, then it will be 6 plus something divided by 12. 6 plus something divided by 12. If you don't do anything to the resistor, then you will have 0.5 ampere current. But if you suddenly pull it to the right side, then at that instant, the current will be more than 0.5 because it will be 6 plus some number, positive number, divided by 12, and that is obviously more than 0.5. So that sounds amazing, isn't it? If you increase the resistance, you expect the current to drop immediately. But instead of dropping, it is increasing. Slightly more than 0.5. Then it has to drop eventually, but momentarily it is increasing. So resistance is increased and current increases is the answer. More than 0.5. Yes, any questions? Let me know. Millihenry is a practical value. Capacitor has, what practical values? Micro, nano, pico. For inductor, L, the SI unit is Henry. What is Henry is very easy to tell. Phi is Li. So what is L? L is phi upon I. What is the unit of flux? Harpal?
So Weber.
Weber. Weber divided by ampere. Weber divided by ampere is Henry. And Henry is generally big for L. So millihenry is something which is quite common to see. A 12-volt battery connected to 6 ohm 10 Henry coil. 10 Henry is fairly big. It's not a non-ideal inductor. It has got 6 ohm resistance, but 6 ohm is small. 6 ohm is small, not big. There's a switch. Drives the constant current in the circuit. Constant current has to be a steady state situation. Sudden change if you do, inductor always opposes that. So constant is only possible at steady state. Then suddenly from steady state, switch is opened. Now open means I should be 0, but not possible to have it 0 immediately. Now if you say that, well, I just cut the switch, so current should become 0 at t equal to 0. If that's the argument you are giving, then sometimes when you are using some heavy appliance, see the sparking. For example, when you switch on geyser, watch carefully. You may see some light. You may see some light coming from just where switch is there. From inside the switch, you can see some light coming. That's sparking taking place. So you may think that mechanically you have disconnected, but air is still there, and that air can conduct some current. Switch is suddenly opened. Assuming that it took 1 millisecond. Now, 1 millisecond is small, but still it's some time. It took 1 millisecond to open the switch. Calculate the average EMF induced across the coil. If you want average EMF, just delta phi by delta t. And phi is Li. L doesn't depend on time. So delta applied on Li is basically delta applied on I with L outside. So L is 10. Suddenly opened. So final current has to be 0. Final means after 1 millisecond. And in the beginning, it was a steady state current of 12 by 6, 2 amps. So final is 0, initial is 2 amps, delta is 2, delta I is 2. All this happened in 1 millisecond. Divide by that. Take the mod. If you just want to know the magnitude, see if you are getting 20,000 volt as the answer. 20,000 volt. And this is just a 12 volt battery, car battery. Just a car battery. 20,000 volt.
Yes, sir.
Any questions or we proceed further? An average EMF of 20 volt is induced in an inductor when the current in it is changed from 2.5 amps in one direction to the same value in the opposite direction in 0.1 second. Alright. Find the self-inductance of the inductor. When you reverse the direction of current, then delta I will become 2 times. Firstly, it is induced average EMF. Average EMF means delta phi by delta t. Phi is Li. Then L delta I by delta t. Delta I. Final I minus initial I. If I take final direction of I as positive, 2.5, then initial direction will be minus 2.5. Now, if you ask that, well, I is not a vector, then How can delta I be I minus minus I? Well, it's because I is deciding the B, magnetic field. I is deciding magnetic field. If you take a solenoid and pass current in one way, then magnetic field will be in one direction along its axis. Say it is from left to right. Now you reverse the direction of current through the solenoid. So the magnetic field inside will change direction. So while you are playing with a scalar, you are influencing the direction of vector. So please make a note of this point and rest putting numbers and calculating. You should be getting 0.4 Henry. Any questions? Let me know. A magnetic flux of 8 into 10 to the power minus 4 Weber is linked with each turn of 200 turn coil. So for 200 turn coil, it will be 200 times that. When there is an electric current of 4 amperes in it, calculate the self-inductance of the coil. Formula based question. Phi equal to Li. Only thing you have to be careful is about information given is for each turn, and there are 200 turns, so the total flux will be into 200. That's it. The rest is simply putting the numbers and calculating. I is 4. See if you are getting 4 into 10 to the power minus 2 Henry. Any questions? Let me know. I hope you remember RC circuit discussion. In RC circuit discussion, capacitor was not letting current after it was fully charged. Capacitor would simply block the current when it is fully charged, because capacitor is what? Two plates which do not touch each other. So two plates that do not touch each other, how can current pass through that region? So it was a block for the current. Capacitor was a block for a current at steady state. But initially, if you connect an uncharged capacitor to a battery with resistance, then capacitor will get charged. When capacitor is getting charged, again the two plates are isolated. The charge is not jumping from one plate to the other, but still we visualize it as a current, right? But there is no charge jumping even during charging. No charge jumping in between the plates, that region which is in between the plates. But there is current, we say, because charging involves charge transfer. In case of inductors, you always have a closed loop. I mean to say, inductor doesn't have a blockage like capacitor has. But inductor does not like change in current. Inductor does not like change in current. So if you have a circuit like the one shown on the board, initially battery, resistance, inductor, and some switch, and you press the switch. Inductor was having zero current. Battery would like E by R current immediately. E by R current immediately. But inductor won't like it. And how much inductor opposes, that depends on di by dt. How rapid is the change in current? The rapid is the change induced is as it becomes higher. The more quickly you change current, di by dt becomes high. Higher is induced EMF. So if switch was off and you put it on instantly, it's like telling inductor that current was 0, now it is E by R. That's asking for too much. 0 to suddenly E by R value, and that makes dR by dt extremely high. Extremely high. dR by dt extremely high. So inductor acts as a strong battery the moment you press the switch on and completely blocks the current. No current at t equal to 0. It should have been E by R. If inductor were a straight wire, it would have been very close to E by R. But because of coiling magnetic effect, it is 0. But then inductor eventually behaves as a straight wire eventually. At steady state, inductor and a straight wire, no difference. Ideal inductor and straight wire, no difference at steady state. So current eventually will become E by R, but it will become after some time, because inductor does not like instantaneous change in current. So it delays the process and E by R is established after some time. Now, inductor may not be an ideal inductor, so that's okay. In that case, whatever resistance it has, that can be clubbed with that capital R. Or even it is possible that even there is no resistance in the circuit at all, no external resistance in the circuit at all. And whatever resistance is there in the circuit, that is due to the inductor. In that case, we can visualize an ideal inductor in series with some resistance, which in reality is due to its own. Right, so you can take an ideal inductor and have an external resistance R, or you can have a real inductor with external resistance R, in which the two resistances will have to be added, or you can have just one real inductor. And if you have only the real inductor, then that can be visualized as an ideal inductor with some R of its own. Now let's do the math. There are two cases, just like in capacitance discussion, RC circuit, there was charging, there was discharging, two cases. Here there is growth and decay. These are the two cases, growth of current and decay of current. Inductor doesn't like any of these two. It just wants constant current. So let's first talk about growth. Let's say at any time t, current is like this. We will use a mathematical approach. So I'm putting plus sign here, and I'm writing E induced as minus L di by dt. I is the instantaneous current. This has been closed at t equal to 0. Applying the loop law, we get, these are the two batteries in series. So E plus minus L di by dt, E plus E induced is this plus here minus here, E plus E induced is equal to IR. You can check this application of Kirchhoff's law. But E induced itself is minus L di by dt. Don't think that minus sign will mean minus all the time. Minus and minus can become plus. So E induced is minus L di by dt. This is the differential equation. L di by dt is E minus IR. In fact, separating is straightforward, no complication at all. L di upon E minus IR equal to integral dt. When time is 0, current is obviously 0. And when time is t, let the current be I. Put the limits of integration and simplify. Just see if you are able to get this thing. I equal to E by R 1 minus E to the power minus T by L by R. T by L by R.
Yes, sir.
Any questions? Let me know. Now, looking at the final equation, what do you think is the unit of L by R? I repeat, what do you think is the unit of L by R? L by R. Or dimensional formula.
It's equal to time.
Time. Unit is second. Common unit is second. Dimensional formula is m to the power 0, L to the power 0, T to the power 1. Why is it so? Because in the power you cannot have any unit. So time has some units, so that must be cancelled by whatever is there in the denominator. T by whatever is here. It is L by R. L by R must cancel the unit of T. Second should cancel second. If it is minute, you should cancel minute. Dimensional formula must be just T. Now watch it carefully and you realize that e to the power minus something is a decreasing function. E to the power negative is a decreasing function. So 1 minus that will be an increasing function, isn't it? Let's put the graph first. E to the power minus x I will plot first. You know it, of course, decreasing function. Now 1 minus that, look at that, increasing function. So 1 minus e to the power minus T by L by R. That is an increasing function. E is the EMF of the battery. R is the resistance in the circuit. Constants. E by R is a constant which is multiplied to something which is rising and rising and rising and eventually attaining its peak. So I is an increasing function. Current will increase. Now that's not a surprise. You have battery, you have resistance, current has to increase if it was zero earlier. But it's not increasing rapidly. If you put t equal to 0, it's e to the power 0 type of thing, which is 1, and 1 minus 1 is 0. So at t equal to 0, you find that current is 0. Now that's very interesting. A battery is there, resistance is there, a closed loop is there, still no current at t equal to 0. And that's thanks to that inductor blocking completely at t equal to 0. But then it increases. So at t equal to 0, an inductor is an open circuit. It won't allow. But when you put infinite for t, e to the power minus infinite, e to the power minus infinite, 0. So I is E by R. Now this is what we would have expected in current electricity, resistance, battery, E by R. But this is happening at t equal to infinite. That's due to the inductor. Yes, practically infinite doesn't mean infinite time. Practically infinite means quite small actually for LR circuit. But nevertheless, delay is there. At t equal to 0, it is not E by R. What happens after a long time? E by R becomes constant, remains at E by R. You can remove inductor, it is of no use. Induction idea is basically whenever there is change. Even Faraday's law, if you think about coil and a magnet experiment, if magnet is fully inside the coil, what happens? Nothing. As long as something moves, some flux change is there, current can be there, or induced EMF can be there, or induced field can be there. So inductor is very much there, but it is of no use as far as this effect is concerned. It will just act as a straight wire after a long time when there is no change. Yes, any questions? Let me know. We stop at this point.